Okay, so we did electron configurations in class, and for some of those, they were getting really, really long, and you guys were getting really annoyed, and I kept saying that there's a shorthand, so I'm going to show you the shorthand. It's called core notation. Sometimes it's referred to as short notation or noble gas notation, so let's see what that looks like. So first off, I want to just write out some plain electron configurations for some of the noble gases. So here's the diagram we used in class, and let's start by just writing out the number of electrons we've got. So neon has atomic number of 10, argon has atomic number of 18, and krypton has 36. So these are all stacked right on top of each other on the periodic table. So starting off with neon, we'll start following our arrow like always. So 1s2, after 1s comes 2s2, so I've used 4. After 2s comes 2p, which can hold 6. So 2 plus 2 is 4, 4 plus 6 is 10. So that's neon. All right, argon. Well, I know argon uses at least as much as neon. So I did these, make it a little faster. So that's my first 10. After 2p, I follow my arrow down to 3s. So 10 plus 2 is 12. After 3s, I zip over and follow to 3p. So I'm at 12. I need 6 more. 3p6. Okay, krypton, 36. Well, again, it's at least going to use what argon has. 1s2, 2s2, 2p6, 3s2, 3p6. So that's 18. After 3p, follow the arrow down. I'm using 4s. That's 2. 18 plus 2 is 20. From 4s, I loop back up to 3d. That is 10. So I've gone from 20 plus 10 to 30. It's a big jump from 3d to 4p. And I was at 30. I need 6 more. Okay, so I want to point something out here with what I have done. So first off, I want you to notice that these all end in P6 with 2p6, a 3p6, and a 4p6. If you look on your periodic table, you will notice that neon, argon, and krypton, being noble gases, at the far right-hand side of the periodic table. And you will notice that neon is the second noble gas down, and argon is the third noble gas down, and krypton is the fourth noble gas down. So what I want you to notice is that I was already kind of doing this, but argon, well, argon has neon right there in the middle of it, right? That's neon. It's right there. And I can put neon in brackets, and that's going to store those 10 electrons. Then I can just figure out from there and do 3s2, 3p6. Or here with krypton, I see argon right there, and I can say, well, argon in brackets stores my first 18 electrons. And then from there, I just follow my diagram and finish off the configurations. So if you remember that the noble gases are always going to end in this P6 column, well, that starts making life really easy, because if your noble gas is here, that means your next element always starts with an S. Okay, so I'm going to show you this a couple of different ways. Okay, so let's do a couple of these. All right, so we've got sodium. Sodium has 11. Well, 11 is more than 10, so I'm going to start off and say I am storing my first 10 electrons in neon. This stands for 10. I need one more. What comes after neon? Well, neon ended in 2p6, so the next thing is 3s1. 10 stored here plus 1 gives me my 11. Shorthand for sodium. All right, sulfur. Sulfur is 16. Well, I can't use argon yet because that's more than 16. So I have to use neon again. So again, neon stores my first 10. I know that neon ended in P6, so I'm going to jump down to the S. 3s2, so that's 10 plus 2 gives me 12. And after 3s, takes me up to 3p. And p can hold 6, but I have 12, and I only need 4 more. So that's sulfur. 10 stored plus 2 plus 4 gives me 16. All right, manganese had 25. Well, 25 is over 18, so I'm now going to store 18 electrons in argon. So that's 18, and argon ended in 3p6, so my next one goes down to 4s. That's 2, so stored of 18 plus 2 gives me 20. I have 5 more, and after 4s I follow 3d, and I have 5 in there. Okay, moving down. You guys yelled at me about antimony, SB, because it had 51. And that did not seem fair, and it was kind of mean. But 51 is larger than 36, so I'm going to use krypton to store those 36 electrons. Krypton ended in 4p6, so that takes me down to 5s2. So a stored 36 plus 2 gives me 38. 5s takes me up to 4d. 4d10, well, 38 plus 10 is 48. Well, I'm a lot closer now. 48 to 51, I only need 3 more. 4d, I followed that up with 5p3. So stored 36 plus 2 is 38, 48, 51. So let's show you something on the periodic table. So here is the, so here, sorry, technical difficulties. Okay, so here's the neon, and the argon, and the krypton. And these all ended in 6, right? And I said neon was the second element down, 2p6, and 3p6, and 4p6. So xenon, what do you think it's going to end in? 5p6. And radon, it's going to end in 6p6. And oganesson, which isn't even on your periodic tables because they're a few years old, is 7p6. These are all 6. They're all p. And I do want you to notice that in this chunk of the periodic table, and I'm going to leave helium off, I'll explain why, there is 1, 2, 3, 4, 5, 6 columns. So this whole region here is called the P block. And everything in this column ends in P1, and P2, and P3, P4, P5, and as we sit here, the noble gases end in P6. Now helium doesn't because it only has 2 electrons, so it's a little different. So what you're going to see now is that the periodic table, it's all in regions of electron configurations. Right here, this is S block, because everything here ends in S1. Everything here ends in S2. That includes helium. Helium here ends in 1s2, just so you know. Okay, well, we've got 2 more blocks to figure out. We've got this block, well, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is D block. And that is in D1, D2, 3, 4, 5, 6, 7, and all the way over D8, D9, D10. And those 2 little funky guys at the bottom, well, those are what we refer to as F block. Because if you count across, you have F1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So the F block is kind of shoved in here in the middle, and it depends on what periodic table you're looking at, but they do some kind of weird things as they stick it in here. But do remember, if you notice barium, that's element 56. The next element, 57, it's typically down here. So you got to remember to zip down. Okay, so the only thing that doesn't maybe quite make sense is where did these numbers come from? The 1, 2, 3, 4, 5, 6. Well, if you've never noticed, on the left-hand side of your periodic table, you have a set of things called period numbers. We've used the groups across the top, but these are period numbers. And those period numbers tell you the energy levels. Tell you energy levels in S and P, right? So 1s1, 1s2, 2s1, 2s2, 2p6, 3s2, 3p6, 4s2. So what happens when we jump into D block? We go down, because remember, after 4s comes 3d, 10, 4p6, 5s2, 4d10, 5p6, 6s2. Whoop, I jump down here, 4f14, back up, 5d10, 6p6, 7s2, jump down here to 5f14, 6d10, and ending in 7p6. That's the magic of the periodic table. So, what does that look like? Well, on my magical mini periodic table here, it's got the same thing. So, tungsten. Tungsten is element 74, and it's right here, I promise you. So, I'm going to use the noble gas that came before it to count for all of this stuff. So, the noble gas that came before it is xenon. So, I can store 54 electrons in xenon. Oops, not by writing that, but by writing this. There we go. Do it right, Michelle. Okay, 54 electrons there. And after xenon, well, that's 54. 55 is right here. That's S block. That's the 6th one down. So 6s2, that would be 56. And then here, that tells me to jump down. That's 4f14. So that's 56 plus 14. I'm at 70. I zoom all the way across, back up to here. 1, 2, 3, 4. And that is 5d4. And that's tungsten. Okay, barium. Well, barium was at 56. So that'll be easy. So I can use xenon again. Store my first 54 there. And again, I picked xenon because it's the noble gas right before it. And then that's the 6th one down. So that is 6s2. And that's xenon. Or that's barium, 56. Okay, polonium. Polonium is over here somewhere. I believe it's right there. It's got 84. So 84 is not quite to radon. So I can store my 56 there. So that's 56 in xenon. And again, following down, 6s2, 4f14, 5d10. I cannot do all of that, right? So I'm here. So xenon, 6s2, 4f14, 5d10, and I have 1, 2, 3, 4 spaces more to go. It's in the 6th row. In the P block, it's the 4th one over. That's polonium. So that's how you do this thing. We'll go over it more in class. One last thing to talk about. Paramagnetism. It's a little weird. It's the only reason we really pay attention to orbital diagrams. So paramagnetism, it is a specific type of magnetism that occurs when you have unpaired electrons in an orbital. So remember the empty bus seat rule? Here's why we care about the empty bus seat rule. Okay? So here's an example of an orbital diagram. So I can only have paramagnetism when I have electrons, unpaired electrons in like P or D, or if this was even higher, if I had F. So, for example, calcium. Well, what does calcium's thing look like? So calcium, it's got 20, so I can store in argon, right? Like that. That's 18 argon, and then it would be 4s2. If you wrote it all out, 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2. So this 4s2, well, s only has the one orbital. So that's going to be an electron up and an electron down. So this is not paramagnetic because these are paired. So it doesn't count. So let's look at another thing. Nitrogen. Well, nitrogen. Nitrogen has 7. Well, let's just do the whole thing. Okay, so it's got 7. So that's 1s2, 2s2, that's 4, 2p, 3. So let's see here. The only thing I care about is this. 2p. 1, 2, 3. Empty bus seat rule. These are unpaired, so this is paramagnetic. Paramagnetic.